Good morning everyone. Myself Kumodni and my roll number is 225085 and topic for the presentation is dual space, contravariant vector, covariant vector and mixed tensor of type 1, 1. So first, what is vector space? A non-empty set phi not belong to V of vector is said to be very small over field F with respect to two operations. First is vector addition, second is scalar multiplication. For vector addition, for every u comma v belongs to V, then u plus v also belongs to V. For scalar multiplication, alpha belongs to F and u belongs to V, then this implies alpha dot u also belongs to V if it satisfies following properties. V plus is an abelian group, alpha comma beta belongs to F and u comma v belongs to V. Then alpha plus beta in bracket multiplied u is equal to alpha dot u plus beta dot u, where u plus v dot alpha is equal to u dot alpha plus v dot alpha. Alpha beta dot u is equal to alpha in bracket beta dot u. The third property is 1 dot u is equal to u, where 1 is unity with respect to second operation. Now, the basis of a vector space. If V of F, then beta is called basis of V if beta is linearly independent and beta span V. That is, L of beta is equal to V of F. Dimensions V over F is equal to number of elements in basis, and V and Vs, that is vector space, and E1 comma E2 comma dot 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 En is the basis of V and lambda belongs to V. Then we write lambda is equal to lambda 1 E1 plus lambda 2 E2 plus lambda 3 E3 plus dot 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 lambda n En is equal to lambda I Ei, where lambda I is component of lambda with respect to basis Ei. Now, change of basis. If basis Ei and basis Ei dash are two bases of vector space V, therefore Ei basis of V, this implies Ei belongs to V. Every Ei dash is a linear combination of Ei. Then we write Ei dash is equal to P I dash Ei, where I dash is n cross n non-singular matrix, that is its determinant is not equal to 0. Similarly, Ei is equal to I dash Ei dash, where I dash is a non-singular matrix. Now, what is contravariant vector? If V is vector space over a field of real number, if M belongs to V and C infinity of M is the set of all differentiable function in neighborhood of M, then a vector lambda is such that mapping lambda C infinity of M is belong किस में होगा R में, and satisfy following properties. First, lambda in bracket F plus G is equal to lambda of F plus lambda of G. Second, lambda in bracket F G is equal to f of m lambda g plus g of m into lambda of f. And third is lambda in bracket af is equal to a lambda of f, such that f comma g belongs to C infinity of m and a belongs to R. The set of such type of vector defined above is denoted by mm, which forms a vector space with respect to two operations. Lambda plus R into f is equal to lambda into f plus mu into f. Second, a lambda into f is equal to a lambda into f, such that lambda 1 mu belongs to mm, f belongs to C infinity of m and a belongs to R, is called space of contravariant vectors, and vector of this space is called contravariant. Now, law of transformation. Let mm be space of contravariant vector of bases ei and bases ei dash are bases of mm and lambda belongs to mm, where lambda I and lambda I dash are components of lambda with respect to bases ei and ei dash. This implies lambda is equal to lambda I ei and lambda is also equal to lambda I dash and ei dash. This implies lambda I ei is equal to lambda I dash ei dash, because ei is equal to pi dash I ei dash. Then from here we can write lambda I pi dash ei dash is equal to lambda I dash ei dash. Then टेकिंग कॉमन, इसको इधर ले आएंगे, फिर इसमें से हम कॉमन ले लेंगे ई आई डैश को. सो वी गेट लैम्डा आई डैश माइनस लैम्डा आई पी आई डैश कॉमन ई आई डैश इज इक्वल टू 0. सिंस ई आई डैश इज नॉट इक्वल टू 0, देन lambda I dash is equal to lambda I pi dash. This is a law of transformation, and parallelly lambda I is equal to pi dash I lambda I dash. Now, what is covariant vector? Let mm be space of contravariant vector mu such that mapping mu mm arrow r satisfy following properties. Mu into a lambda plus bv is equal to a mu bracket lambda plus b mu in bracket v for every lambda comma mu belongs to mm and a comma b belongs to R. The set such type of vector defined above is denoted mm star and from a vector space with respect to two operations defined as first mu plus s into lambda is equal to mu in bracket lambda plus s in bracket lambda, and second a mu lambda is equal to a mu in bracket lambda, such that mu comma s belongs to mm star and lambda belongs to mm and a belongs to R, is called covariant vector, and vectors of mm star are called covariant vectors. Now, the dual space. Since we know that mm of R is the space of contravariant vectors, let mu be a function mapping mm arrow R such that for all lambda comma mu belongs to mm and a b belongs to R. Then mu in bracket a lambda plus bv is equal to a mu in bracket lambda plus b mu in bracket v. Then u mu is called a real valued linear function of mm in R. Let mm dash be the set of all such real v-valued functions. We define vector addition on mm star as follows. For every mu, comma delta belongs to mm star and lambda belongs to mm. Then mu plus delta into lambda is equal to mu lambda plus delta lambda. इसको इक्वेशन 1 हम लोगों कंसिडर कर लेंगे. Then defined scalar multiplication between mm star and R as follows. For every mu belongs to mm star and lambda belongs to mm and a belongs to R, then क्या होगा? a mu lambda is equal to a mu of lambda. इसको इक्वेशन 2 कंसिडर कर लेते हैं. It can be shown easily that mm star of R is a vector space under vector addition and scalar multiplication defined by 1 and 2 respectively. We call mm star of R the dual space of mm of R. Now the next topic is mixed tensor of type 1, 1. Since Tij component of vector belongs to mm cross mm star with respect to basis ei and Ti dash j dash component of vector belongs to mm cross mm star with respect to basis ei dash are related as Ti dash j dash is equal to Pi I dash Pj j dash Tij. This is mixed tensor of type 1, 1. Thank you.